At the very front of logical headway is the European Committee for Atomic Examination, CERN, prestigious for its pivotal commitments to molecule material science. As of late, the widely popular Molecule Material Science Research Center has uncovered an incredibly interesting finding from its Huge Hadron Collider that could totally change how we might interpret the universe. Researchers believe these unusual discoveries could uncover the presence of extraterrestrial life in an equal reality. This noteworthy thought has started energy and serious conversation among specialists. Could this amazing disclosure reshape how we might interpret the universe? Furthermore, whenever confirmed, what significant experiences will this disclosure offer into the nature of reality itself? Join us as we dig into the recently published discoveries, investigating how CERN researchers are ending their silence on this chilling new disclosure that has the potential to change all that we know. The European Gathering for Atomic Research, also called CERN, has been well known for its thrill-seeker tests since its origin during the 1950s. It has been at the center of attention several times for good reasons, but its investigations have excited concern about the potential arrangement of dark openings, fractures in our reality, and numerous other dangers. One of CERN's most well-known and disputable accomplishments was the development of the Large Hadron Collider, LHC. The LHC is the world's largest atom smasher. Starting its procedure on September 10, 2008, it remains the latest expansion to CERN's accelerator complex, crossing more than 27 kilometers of superconducting magnets and a progression of speeding up gadgets. The CERN Super Collider cost more than $4.5 billion. Many would argue that this money was carefully spent since the LHC has resulted in some of the most significant discoveries of the last few decades, such as the discovery of the Higgs boson and numerous other previously obscure particles. This tremendous machine is capable of speeding various particles around the circle until they reach close to light speed and complete more than 11,000 laps. The LHC does this with a series of extremely strong electromagnets that produce a magnetic field inside the accelerator that is nearly 100 times more powerful than the field that surrounds the Earth. Some have expressed concern about the effect of creating such areas of strong magnetic fields on nearby gadgets, as well as its impact on the Earth's own field. Once these particles reach their maximum speed, multiple times the speed of light, particles heading in opposing directions are compelled to meet in a violent crash, delivering tremendous energy and a variety of particles. When particles impact, a surge of particles escapes out in all directions, with most of them enduring only parts of a second before blurring. Changing the source of particles allows scientists to uncover new particles in this whirlwind. Extraordinarily sensitive indicators are placed around the crash sites to record all the data from each crash. This amount of information mounts up rapidly and requires a huge amount of time and work to process. The LHC's investigations produce more than 15 petabytes of raw data from these crashes, which need to be purposefully filtered to extract the information the scientists need. In 2017, the LHC achieved a significant milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this amount of data into perspective, 1 petabyte is similar to around 250,000 movies. But what exactly are they searching for in all this data? They identified something happening with a particular type of stopper or quark. Quarks are the crucial building blocks of matter and exist in various flavors, as defined by physicists. Some of these quark flavors are entirely unstable, decaying into different particles in the blink of an eye. The beauty quark, with an average lifespan of 1 in 1.2 trillionth of a second, became the center of attention due to a particular distortion. Its decay pattern differed from what researchers expected based on the standard model. According to their expectations, when a beauty quark decays, it will be affected by the weak force and transform into a set of lighter particles known as leptons, either an electron or a muon, with the standard model predicting a 50-50 chance for the two particles. However, the LHC data revealed that these quarks decayed into muons 70% of the time as opposed to electrons. This divergence could exist if a previously unknown type of particle is involved in the process. This has led some scholars to speculate that a new kind of physics might be at work. A new force-carrying particle would imply entirely new physics that could extend the standard model and answer many confounding questions. The possibility of new physics challenges the standard model theory, which provides our best understanding of how the odd universe of particles behaves. The Standard Model is a scientific framework that precisely explains every aspect of our understanding of the physical world's building blocks. The shocking thing is that, despite this level of precision, physicists are well aware that this model is incomplete. The Standard Model only describes three fundamental forces: electromagnetic force, strong force, and weak force. Currently, there is no representation of gravity nor an explanation for dark matter, the universe's most prevalent form of matter. During recent experiments, scientists found an anomaly in the data they were analyzing that differed from the Standard Model's expectations. Although it is not uncommon to find results beyond this framework, given the volume of data produced by the LHC, this time something piqued scientists' interest, and they saw the need to investigate further. What might this new force be? To explain this unexpected discovery, the scientists proposed the existence of a new fundamental particle, which they refer to as Z prime, a force-carrying particle. Although this force is the best bet, it is very weak, as no indications of it have been found so far. The researchers believe it could interact in a unique way with electrons and muons, but the extent of its interactions with Standard Model particles remains unclear for the time being. If researchers were to discover new force-carrying particles, it would be a 10-year hotly anticipated breakthrough in physics. Physicists believe that if this discovery is confirmed, it will help unravel well-established mysteries of the universe and make sense of old problems, such as what dark matter is and the role of the Higgs boson in the present day. Some researchers believe that this unseen force could help fulfill one of physics' most significant objectives of the last century: binding together the fundamental forces of existence. According to Elon Musk, CERN built the largest and most powerful energy molecule collider in human history, the Large Hadron Collider (LHC). Between 1998 and 2008, more than 10,000 researchers from many institutions and labs from over 100 countries assisted with this process. It sits within a 27 kilometers long tunnel on the border between France and Switzerland, near Geneva, around 175 meters underground. The very first impact recorded at the Large Hadron Collider had an energy of 3.5 tera-electron-volts per beam, multiple times that of the previous world record. The energy reached 6.5 tera-electron-volts per beam once the LHC was further improved. Musk noted that the LHC excels at proton beam impact. Moreover, it can accelerate lead-on beams, specifically proton and lead collisions, which are typically conducted for 1 month for researchers testing the predictions of several particle physics theories. The primary goal of the Large Hadron Collider is to test the properties of the Higgs boson and search for the large array of new particles predicted by subatomic particle theories. Hadrons are composite subatomic particles made up of quarks, which are held together by a strong force, much like how particles and atoms are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons that are widely recognized, including the pions and kaons, which were first discovered in cosmic ray tests in the late 1940s and early 1950s. The LHC brings two colliding particle beams together so they can interact. The Higgs boson is thought to be a fundamental particle associated with the Higgs field. It is the quantum excitation of this field, much like how you notice waves in the ocean. The boson is like a new species in the particle zoo. It lacks the quantum characteristics of key matter, as well as the carriers of quantum interactions like electromagnetic force, weak force, and nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a groundbreaking discovery accomplished simultaneously by the two major multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012 at CERN. At the time, the new scalar boson was found mainly in two rare decay channels that provided the clearest signal: decay into a pair of photons, which required an entirely quantum virtual process, and direct decay into a pair of Z bosons, the carrier of the neutral-weak interaction. Although the discovery of the Higgs boson at the time established the Standard Model, examination into this elusive particle did not end there. One of the main discoveries since 2012 was the confirmation of Higgs decay. According to CERN, the study of this elusive particle would continue to evolve during the LHC's third cycle, particularly once the particle accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, providing researchers greater opportunity to detect strange physics, such as events that do not fit into the Standard Model. CERN estimates that when the accelerator is upgraded each year, it will produce 15 million of these particles. This compares to the LHC's production of 3 million Higgs bosons in 2017. This may be helpful for identifying different kinds of Higgs boson theories that go beyond the standard model of particle physics. Expect up to 5 distinct types of Higgs bosons, some of which may be produced less frequently than the basic Higgs. Even before the enhancements, researchers have provided compelling evidence for a magnetic Higgs boson. But why does this matter? The Higgs field was enormously significant in the early times following the universe's creation. It dictates the very nature of the vacuum that exists in our spacetime. It allows matter and interactions to exist as we know them, as well as the development of mass in all known fundamental particles. Without the Higgs field and thus the Higgs boson, the universe would be devoid of any atomic components, stars, and life. Why do you think the Higgs boson is called the God particle? Popular media helped cement the Higgs boson moniker after its discovery. It is most often traced back to Nobel Prize-winning scientist Leon Lederman, who out of frustration referred to the Higgs boson as the goddamn particle, since it was so difficult to detect. According to Business Insider, when Lederman wrote a book about the Higgs boson in the 1990s, he wanted the title The Goddamn Particle, but the publishers disagreed and changed it to The God Particle. That was the start of an issue between the particle and religion that continues to concern current physicists. Nonetheless, it is hard to underestimate the significance of the Higgs boson and the Higgs field because only particles would have mass under this part of nature. This suggests there would be no stars, planets, or people, which might help explain its blustering moniker. Aside from the clear need to describe the new particle, researchers continue to investigate the Higgs boson for 2 reasons. First, they need to know how the physical vacuum we live in began in the early universe. Second, they need to know how this physical vacuum can remain stable. The Higgs field is unique in that it sends non-zero mean expected potential energy to the physical vacuum. This is what has a major impact on our universe. Researchers believe that accessing the structure of this energy potential is responsible for the existence of electromagnetic force with infinite reach and weak force with a very short range. To do this, scientists must explore how Higgs bosons interact with one another, and for that, they need to create pairs of Higgs bosons. The Higgs boson contributes to the answer to the fundamental question of how all other fundamental particles get their mass. However, its mass is yet to be explained. Any imbalance in the theory doesn't account for this mass and causes accidental instability. Quantum variations could disturb the vacuum itself. Luckily, this occurs on timescales much greater than the known lifespan of the universe. However, researchers are still searching for additional Higgs boson-like particles that would indicate the presence of new physics needed to settle the Higgs boson mass. All these considerations fuel the investigation of even more data, and if possible, access to greater collider energy. This is why, 10 years later, many scientists worldwide remain focused on the work. The Higgs boson was first proposed in 1964 and discovered in 2012. Scientists have questioned why it took so long. This is because the Higgs boson is both massive and incredibly unstable. To create such a massive particle, scientists needed to concentrate a tremendous amount of energy in a small container. They required a high-energy collider. Once formed, Higgs particles disintegrate in a variety of ways, with only a small fraction detectable from the background. Researchers built the largest and most complex detectors to identify such particles. Then, they analyzed many billions of proton collisions to find a Higgs boson signature. Anyway, will CERN's operations and discoveries empower us to make huge disclosures? Will it send us to our ultimate end? Scholars have 3 main theories about what CERN is up to. The first and deadliest thought, which has made some point fingers at CERN, is that the organization is attempting to open a doorway to hell. Some believe that CERN's experiments with subatomic particles flying at the speed of light will propel humanity beyond the gates of the last hell. Continuing with the exploration of CERN's cutting-edge research, the potential implications of their discoveries are vast and far-reaching. As scientists push the boundaries of particle physics, there is a growing focus on understanding the very fabric of reality. One area of immense interest is the concept of quantum entanglement. This phenomenon occurs when 2 particles become linked in such a way that the state of one instantly influences the state of the other, regardless of the distance between them. This has led to discussions about the nature of space and time and the potential for faster-than-light communication. Furthermore, CERN's research may uncover deeper insights into the so-called multiverse theory, the idea that our universe is just one of many, possibly with different physical laws or dimensions, is gaining traction. If proven, this could radically alter our understanding of existence itself. Additionally, the continued exploration of dark matter and dark energy, which together make up about 95% of the universe's mass and energy, remains one of the biggest challenges in modern physics. Understanding these mysterious entities could lead to a new era of technological advancements and open doors to a more unified theory of everything, reshaping our place in the cosmos.